welcome to another Tech Talk. I'm a data scientist at Qimia, and today I would like to talk to you about variance in data science. You might have encountered this before. You run an analysis or train a model and you get a certain result, but if you look at it again, you get something different. Maybe the difference is just by a little, or it might be by quite a lot. But this brings all your findings into question, because how can you be sure about what you got? Maybe the next time you look at it, you get something completely different. So how can you approach this problem? Step one is always to make your variance visible. This is done by running your experiment multiple times and checking how strongly the individual measurements deviate from each other. This is called the standard deviation. Then once you calculated it, you put this deviation next to your actual measurements. The good news is we already have multiple measurements. Each point in our test set is such a measurement. And when we calculate a performance metric like an F1 score on accuracy, we calculate an average across all these measurements. The only thing we need to do then is to also calculate the standard deviation and put it next to it. This will look something like the accuracy is 91 plus minus 2%. Statistically, this means that 68% of our measurements should be between 89 and 93%. Now, if somebody else measures 92 plus minus 2%, we are still well within what we would expect, while if somebody measures 80 plus minus 1%, these two measurements are not really compatible and we know that something must have gone wrong. This can have very big effects on your decision making, because an accuracy of 70 plus minus 1% is a very different result than 70 plus minus 30%, and you might not want to put the latter one into production. In this way, the error estimate is an estimate of risk, because you can be sure that your model will always be in the area of error you calculated. And of course, you really want to be able to estimate this risk before putting anything into production. So once you calculated your errors, you run into another problem. What if, for example, you define an acceptance threshold of 75% and your measurement is within this one standard deviation? For example, you define an acceptance threshold of 75% and your model is 76 plus minus 1%.
According to what we said before, this means that there's an 82% chance that your model is good enough and an 18% chance it isn't. In most sciences, you expect at least 3 standard deviation as a rule of thumb. So maybe you're thinking this is not good enough. So what can we do?
First, you can use a larger test set. This can be done by gathering more data, which is probably a good idea, but it's not always possible. Another option is to increase the fraction of your test set, which is usually chosen about 1/3 of your data size. And that's for good reason. If this seems too much for you, or you're thinking you have very little data already, consider that the accuracy you'll be calculating is an average, and the error of an average is proportional to 1 over square root of n. This means that especially if you have very few points to work with, adding these few points to your test set will increase the accuracy of your performance metrics a lot, while adding the same few points to your training data set will only increase your model performance slightly. And once you're sure that your model does what you want it to, there's nothing stopping you from training your model again with all the data points, because now you can be sure that the performance of the model is between the boundaries you calculated previously. Another option is to perform the training multiple times and averaging the result. This, of course, will introduce another average, which will produce another factor of 1 over square root of n in your error calculation. But if you use the same data over and over again, you're kind of ignoring the fact that in the real world, you never look at the same data twice. A better option is to use cross-validation, which I cannot explain here, but which will in fact use your entire data set for validation. The third option is to use ensemble methods. This means you train a model multiple times and average their predictions. This can either be the same model or it can be different models, but by introducing this average, the predictions themselves become much more stable and your variance reduces. Lastly, overfitting is one of the biggest sources of randomness. This is because there's not only one way of overfitting, but an infinite amount. This can be clearly seen here, where we trained the same model twice on the same data, and you can clearly see that both sides overfit, but they overfit in a very different way. This can, in the worst case, lead to your model performing very well in one try, where it maybe fits the specific test set you've chosen very well, but much worse the next try. And then if you use standard overfitting reduction methods like regularization or dropout, this will, on one hand, improve your model performance, but on the other hand, also reduce variance. And by doing that, this is a clear win-win situation if that's the case for you. Before ending, I would like to say one more thing. Fixing a random seed is not really an option here, because while it will remove all variance during training, once you let your model out into the real world, you'll get back all the randomness, and now you have no idea how big it is. So it's much better accepting the randomness, evaluating how big it is, and estimating the risk. As a conclusion, showing your errors is usually a quick thing to do, but it can have a huge impact on your decision-making and business insights, and it can help you estimate your risk and making smarter decisions. Anyways, I hope you learned something new today, and see you next time.
Qimia. To the future, together.